Hi, in the last video, we have created a simple binary search tree based structure, and we have implemented two instance function. One is called add function, and one is remove function. And the remove function makes use of a helper function called find minimum node. And that's what we did for part one. So for part two, what we want to do is I wanted to implement the five traversal types that can be used for binary search tree data structure. And after that, we can also implement the most important function of binary search tree, and it's called the search function. It's a very simple function. But now let's first do the traversal functions first. All right, to start with, we can do a post order traversal. So the post order traversal will first, so the pre, the in, and post, these adjectives, they are describing the root actually, because the left and the right, left always starts before the right, and the root is the one that the ADJ is describing. So the root comes first, the left and right is going to be used by pre-order, and that's going to this algorithm is going to be implemented to every single node inside our tree structure. Let me show you what does it mean. So first, we should declare pre-order and name it traverse, and receive a callback that's going to act on every node, current node. And in there, we can declare a function. Let's call it pre-order. And in there, we can say we must intake the current node, and we pass the first node, root node inside it, and then we can write our method inside the function. So according to this, we should first implement the callback function to the root node. So we should do that exactly. So current node should be used by our callback. Okay, then we can call pre-order current node dot left. So left, after left is going to be right. Yeah, our function is finished. Quite simple, right? Let's test it out. So what happens there? Binary search tree. Okay, it's going to be pre-order traverse. Testing a callback. Let's put in a simple array function, and it's going to console.log v.data. Okay. But okay, first thing first, we should check if current node is equals to null, then we should do nothing. Okay, that will do it. So we should run node binary search tree, and as you can see, our our function has returned these things. 5 was callback, run first, 5 3, then 2, so then 4. So in this case, 5 is the root, go to the left. 3 is also a root for 2, so 2 is left, then go to 4, and then go to the right. 7 is the root for 6, 6 go first, and 8, and we are done. So this is how pre-order works in binary search. So let's move on, and we can implement the same thing for in order, but in order, so the ADJ is in, so left goes first, root goes in, and right goes last. So we can do the same for the in order, but just change the name slightly. Okay, in order traverse, also in order here, and the kernel callback, move the callback inside the second place, and we are done. So let's write. Okay. Let's make this screen bigger. Okay, so in here, let's say left goes first, then root 3 and 4 is the right. So 3 is the left to 5, so 5 goes, and again 6 left goes first, 7 is the root, and 8 right. Okay, so this is how in order works in traverse works in our tree structure. So lastly, we can do post. Post means the root comes last. So we will just say that left, right, root. Okay. So we will just modify the same function, passing post order. Move this to the last position. Okay, we are done. And let's run it. So post order traverse. So it's going to be 2 goes first, then 4, then 3, then 6, then 8, then 7, then 5. So left goes first, then right, then root. So the post order is basically the same to our depth first, but the difference is depth first is used for just the simple concept of children comes first, then root. All right, and so in here, left goes first, root up, left and right is both children, then we will do the callback for the root. So it's the same concept. So the way we can implement depth first in JavaScript in the binary search tree structure is just going to be depth first search. Okay, not search, traverse. Same thing, callback. And we just say this dot invoke post order traverse and passing our callback, and we are done. Yeah. So we have to implement. You don't have to implement this function, but when we do, and when other programmers are using the same code, and they are not familiar with post order traverse probably, or they don't want to use post order, they can use always rely on things that they feel familiar with, and it's crucial to include something like this in your library during collaborations. And for the last part, we can do breadth first search. So breadth first search is probably the easiest, level by level, from left to right. Okay. So the way we are going to do this is not applying the same algorithm to every element inside our tree structure. The way we can do this is okay, have we tested depths? Okay, we haven't. So, okay, we can just test it first. Ensure that we have depths first, traverse. Be sure we have this right solution. Okay, I think it's correct. We can move on. Breadth first, traverse. Okay, takes in a callback. Then, okay, we need a queue. So constant queue equals to empty array passing the root node first. So one element inside, and we need to let what's the thing called again? So it's going to be current node and make it equals to q dot shift first in first out, right? And while our current node is still effective and not undefined object, we can first so if let's say the left current node dot left is not equals to null, then our queue can push the element of the left inside. And let's do the same for the right as well. Okay. And we can do the callback and pass in the current node, and we can update the current node after we do the callback. So q dot shift, and then after this is done, we check the new current node and see if it's valid. All right, our breadth first traverse is also finished. Let's test it. So 5 goes first, then 3, then 7, then 2, 4, 6, 8. That's correct. I think our 5 traversal types are finished. So we can then move on to the last function we want to implement, which is search. So because the way that we implement our binary search tree, search can be incredibly fast and easy. Let me show you what does it mean. What do I mean? So it's going to take in a value as well, and it's going to return a node. Okay. So what we can do first is return. Okay. Can return a function called search node. Takes in a current node. Takes in this dot root. Takes in the root node. And in here we could check if current node is equals to now, then return now. Else if current node, okay, if current node is not now, meaning current node has data, then we can start comparing our input value with our current node dot data. So if value is equals to current node dot data, we return the current node. Else if value is smaller than the current node dot data, meaning it's on the left hand side, then we return whatever is returned from search node, and we pass in current node dot left. And let's do the same if value is bigger than it. Just need to pass in the right. Okay, I think we are finished. And then whatever is being returned in the end will be returned from search. Let's test it out. Search. What do we want to search? So probably 8 first. So it passing the element here without any children, which is correct. We can pass in 7 as well and see, okay, correct. Then we can pass in 5. Yeah, 5 is a node, has a left, which have 2 and 4, and has a right of 7, has children 6 and 8. Also correct. So at last we can test in element that's not inside and have our function returns null, which is designed to do so. So this is typically how we can implement the 5 simple traversal types in binary search tree and implement a search function. And that's conclude our tutorial for the binary search tree. And thank you for watching, and have a good day.